J.G.Kim from South Korea is really happy to give a presentation in here because actually this is my first conference after on-site conference after COVID pandemic. Yeah, it's really happy about that. So today I'll give some presentation about transformation induced plasticity in the heterogeneous structure titanium zirconium niobium tin alloy. Yeah, in situ alloy. Actually, yesterday. In this conference, there are many interesting talks on the ion-based memory alloys by Christian. But in our cases, we developed some titanium-based chain memory alloy for medical devices. So I would like to introduce some specific behavior in the heterogeneous microstructure these alloy systems. So today I briefly introduce the concept of this study and introduce how we performed it and present some experimental results and discuss about it. So yes, I just give introduction about laser-based additive manufacturing because many people already know about it. So I just focus to why we use titanium and the DED for this study. So titanium alloy-based additive manufacturing overcome to limited machinability of titanium, especially for titanium with mixture with refractory alloy has some really poor machinability. So that's why many implant company wants to adapt additive manufacturing. So because of this reason, it is really appropriate to manufacture aerospace or some medical device parts because these are flexible. This process is helpful to manufacture some flexible design and depending on the demand of users, and especially the DED represents some lower manufacturing costs and high processing speed compared with LPBF, though its accuracy is a little bit low. But yeah, the DED, one of the strength points is DED is we can perform some in situ alloying with some elemental powder. Actually, the in situ alloying is quite efficient strategy for developing alloy design, or even we can distribute some particle distribution. Actually, the alloy prototyping by repetitive melting and solidification by high laser beam is quite helpful to make some flexible composition design by melting mixed powder, and it allows to design a heterogeneous microstructure. Even we can disperse some particle in the matrix. But I cannot say this strategy is cost effective because when I starting this work, I just tried to buy some elemental niobium and zirconium powders, and it was too expensive. So that's why I just struggled on my budget during 1 or 2 years. Yeah. Anyways, we start to develop titanium zirconium, niobium zirconium, and tin titanium alloys because although the titanium alloys are quite appropriate to medical devices due to their high strength and corrosion properties, but the present alloy has some several issues, such as some titanium alloy 64 has some limitation to due to the archival species like aluminum, and has some stretch shielding impact due to their high elastic modulus compared with our bone. And titanium nickel chain memory alloy has some limitation due to some allergy by nickel and due to some poor wear resistance. So to overcome this region, in this work we added some niobium and zirconium to reduce elastic constant and increasing wear resistance of each alloy system. So this alloy system has some several interesting properties. Not only has some their outstanding mechanical properties, but also they have some outstanding superelasticity and biocompatibility. So when we conduct some imposing some thermal and mechanical stresses into these alloy systems, they are starting to inducing multiplicity transformation, and it becomes to the beta matrix when we relieve it. So based on this region, this sample represents such kind of superelasticity, as you can see in this on this graph, and such a multiplicity transformation usually observed in the green boundaries where you usually have a high energy, high interfacial energy. So based on these Beijing concepts, so we just thought the additive manufacturing with this alloy system might be really helpful, not only just remove some machinability issue, but also we also did those how the heterogeneous microstructure affects to the Martens's transformation behavior during plasticity formation or some thermal stress. So to achieve this goal, we designed titanium niobium tin zirconium tin alloy system with directed DED machine with some multi-hopper system. So the reason why we did not mix elemental powder before DED processes, we don't want to waste too much elemental powder. As I mentioned before, the powder cost was horrible, and also we can control the feed rate of each elemental powder by multi-hopper system, as you can see in the summarized table as follows. But this is, I mentioned it in the result, EDS result, but this strategy also has some problem because as you can see in the micrographs, you can see the many satellites in zirconium and tin reduce the flowability of elemental powder that makes some big gap between some feed rate and as we expected. But anyways, we just tried that at that time, and some control processing parameters, especially for the laser power, to reduce the to check the Lego fusion and unmultiplied particle changes as we increasing laser power and investigate the grain size and phase distribution. And after that, to correlate, to check the microstructure evolution and mechanical properties, we conducted optical micrograph to check the Lego fusions and unmelted particle distributions. And EDS and EBSD analysis were conducted to check the chemical heterogeneity and on microstructure changes. And to correlate with these results, we perform both hardness and tensile test. So now I show some experimental results. So as you can see in this, in the optical micrograph, the Lego fusion has been drastically decreased after 230 watt cases, but yeah, still lots of unmolten niobium particles were distributed in the matrix. So basically this process was unsuccessful because the laser power of less DED machine was too low to perform to completely melt the niobium particles. However, I'll show it in the last slide. We also performed some additional results in the high energy power DED machine, and that we finally success to melt these niobium particles. But yeah, at that time we failed. And when we check the EBS result, we can see some fully BCC structure because this alloy system has a fully beta phases, and niobium also has some BCC structure. So that's why we can see the fully BCC phase distribution, while the unmolten particles, niobium particles can be distinguished by image quality. And because the laser power spacing is quite small, the grain size change is not significant, so we can ignore some grain size effect in this work. And also, when we check the EDS result, we can clearly see the niobium particles are distributed as follows, while some slight chemical heterogeneity were observed in the matrix. And this kind of, especially for the low content of niobium may reduce the phase stability of this alloy system that accelerates phase transformation behavior more. And even moreover, in case of 230 sample, we can find some low tin content because, as I mentioned in the experimental procedure, we can find some lot of satellites in the tin that reduce the flowability, and some is hard to mix up during additive manufacturing. So because of this region, the 230 sample represents some lower hardness compared to the other samples, while the other sample represents some continuous increment of hardness. And when we check the stress strain curve with 230 and 260, because these two samples represents quite low porosity, we can find 260 sample represents on higher strength and ductility combination than 230 sample due to the reduced Lego fusions and thin content, that provides an interactivity enhancement and additional strain hardening capability. Moreover, when we check the strain hardening curve, we can find some interesting behavior when the has the strain hardening rate increment in doing plastic formation, which usually known as the trip behavior. So we check the tensile deformed microstructure as follows. And when we check the tensile test deformed microstructure, we can find some interesting result in the pace map. When the DCC to magnetostatic transformation occurs near the niobium particles, while the similar pace transformation does not observed in the grain boundaries. So this means we can control the we may control the phase transformation behavior if we disperse some particles into the matrix, which has a higher interfacial energy than that of the grain boundaries. So we just check the details of the magnetostatic marstensite phase more by TEM observation, and we can find these martensites are consist with two variants as shown in the yellow and red images, and we believe the interaction between two variants may also contribute to the extra strain, extra hardening of this alloy system. So first of all, I just summary of the present results. So we design, design heterogeneous microstructure, titanium, zirconium, niobium, tin alloy via in situ alloying, and we check the mechanical property can be enhanced by reducing Lego fusion, and unmolten niobium particle, but they still distribute natural particles. But we also find some BCC magnetostatic phase transformation near the unmolten particles, and then this result shows the phase transformation can be controlled by dispersing particles via additive manufacturing. I think not only just particles, but if we disperse some different spaces into the matrix, we can also control some similar behavior by changing some interfacial energy content condition. And maybe all of you also have some question that it still has some larger unmolten particles, then how about when we reduce them? So we just perform additional experiments by changing some EED machine with high energy capacity and successfully reduce the unmelted particle, niobium particle fraction less than 3%. As you can see, the particles are almost disappeared. And when you check the stress strain curves, we can find some interesting results, especially for case of high energy density results. We can find some quite outstanding mechanical properties. So even we just tested at least 3 times for obtaining reliable results. So so nowadays we just check why these sample represent such an outstanding mechanical properties. Hopefully I just finalize it until the end of this year. This is the end of my presentation. So for details, you can find additional results in the published result. So thank you very much.